All right, ladies and gentlemen, before we get started with our implementation of a proof of concept for BattleBlocks, we need to spend just a moment and talk a little bit about the math we're going to be using. Math. Why are we going to be using math? Well, let's take just a second and look at a box. In BattleBlocks, we're going to be dealing with blocks. Well, when I say the word blocks, what should come to mind is going to be some sort of box, be it, well, a square or perhaps a rectangular shape. Now, I'm sure when you put your game together, your sides are going to be much straighter than mine, but I'm sure we're all in a forgiving mood today because I am working with a Wacom tablet and I'm way away from the keyboard. Now, when our ball is bouncing around the screen, we're going to have collisions between the ball and the sides of our boxes. All the way up to this point, for the most part, all the collision code we've dealt with has been extremely simple. Checking to see if we've, collided with a wall. Okay, well, that's been easy for the screen bounds. Just move it back over, send it back in the opposite direction. Or some of the simple stuff like we did with the Pong game, okay? Once again, relatively simple calculations, but this time around, we're going to need to take into account all four sides of our blocks. And then we're going to need to make sure that we make the ball bounce off of it in the appropriate direction so that it looks right. So that means we need to know, did we hit this side? Did we hit this side, or this side? Now, we're going to demonstrate putting this together in two different ways. One, we're going to start off by using just a simple square. Why? Well, for us, a square works out quite nicely because to keep things nice and simple, you can fit a circle around it. I know that's a beautiful circle. Work with me.
Not only can you fit a circle around it, if you do, all of the corners intersect the circle at equidistant points. That means if you now split up that circle using your new square points, you have equal angles on all sides.
That's right, because that's what it's going to be about in the end, about these angles. As Logan's saying, though, this is what he's talking about. See how we can split that up? Absolutely beautiful. We start off with a 45-degree angle, then we got these 90-degree angles all the way around. And we can use this if we were to pretend that we literally just sliced up our circle. We can check a series of ranges. Really, we're checking a series of angles. Is our ball this area? Is our ball in this area? Is our ball down here? Or is our ball over here? And based off that, then we can take the appropriate actions. Now, we can't really fit a circle around this guy down here. It's a little different. I mean, we're still going to be working with...
We could fit a circle around it, but the angles wouldn't be as useful. The problem is it's that we're not actually using the circle to get the angles. It's that the angles happen to divide the circle equally in the case of a square.
Right. Exactly.
You could still draw the same circle around it, granted it'd be farther from the top and bottom, but if you drew the lines through the corners, you wouldn't have equal points on the circle.
No.
If you drew them through equal points on the circle, you wouldn't be hitting the corners on the box anymore.
Exactly. So we're going to go about handling things a bit differently when working with a rectangular box, where we're still going to have a dividing line right here. But we can still figure out angles because we can easily calculate these corners because obviously we have the width and height of our box and we know where it's located at. And then with this, well, there you go. Now we've got these great triangles that we can use. And with a little bit of trigonometry, we can easily come up with, once again, angles. Okay? And in using these angles, of course, we can now determine what side something is on. Now, this might sound really confusing for those of you that slept through math class. I promise you, it really isn't that bad. Fortunately, we have a method that's going to make things really simple. I just want you to see how things are working so that when we get to it inside our implementation, you go, oh, yeah, that all makes sense. So let's see. Actually, instead of making a new layer at the moment, I'll go ahead and make a new layer. I'll make this as cleanly as I can. So let's go ahead and jump over here. And let's start out by talking about a circle, because he's going to help make everything very clear. So let's see, I can start out somewhere right about here, drag them out about there, and then let's come up here to edit, stroke, and that's good, and we'll deselect, and let's come over here. All right, now let's go ahead and break this guy up a little bit, so something like that. and something like that. And I'll throw in a new layer. Actually, no, not yet. Okay. Now, we're working in screen coordinate space, meaning that on our screen, if I was to draw out our screen here, X increments to the right, so X gets larger and larger and larger, and Y increments as we go down, okay? This is very important because this is flipped from what you may be used to if you're doing just standard mathematics with graph paper, where Y is going to be going up, and once you cross across the x-axis, Y is now going negative, okay? Now, this is also going to mean that our angles that we're working with are going to be different than your standard angle that you may be used to working with in trig. Just keep that in mind. Now, what we're going to do is we're going to manipulate our numbers just a little bit so that we get 0 starting right here. And we're going to go in this direction, and we're going to have it so that as we wrap all the way back up and come back around and close off the circle, down here, we have 2 pi. Now, as we work our way around, every 90 degrees is half pi. So let me go ahead and jot that down. So here we go, 90 degrees, so that's going to be half pi. So 90 more degrees is going to be what? Well, it's 2 half pi's. Pi. That means we have a full pi. So if we come around here down to the 270 mark, what are we going to have? Well, now we're going to have pi plus half pi. Really pretty simple. And let's go ahead and throw a 45 degrees in there, just so that we've really covered everything. So it's going to be a quarter pi. Piece of cake. So this is all about calculating angles. And now when calculating these angles, I'm trying to make that look a little prettier, the number that we're going to get back from atan 2 is going to be radians. It's not going to be degrees. And with radians, well, I don't want to get too crazy of a math discussion. I want to keep this very focused. So what we're looking at is getting these angles, okay? So what I want to do is just come up with a very simple scenario that I can demonstrate here on the whiteboard, and then jump over into Visual Studio and actually use atan 2 to calculate it and give us that number back. So first of all, what does atan 2 look like? It's going to look like this. Tan 2, and the arguments that it's going to take in, very important. Y, then X. Oh, you might be thinking to yourself, wait a minute, that's just a point. How are we going to get an angle from that? Simple. It is a point, and atan 2 assumes that we're working at 0, 0, okay? So assuming that we're working at 0, 0, you give me this point, and hey, I can come up with the angle. And with the little trickery that we're going to do to guarantee that we start over here on the left-hand side, there's not really any trickery to it, it's just a matter of adding pi, which you'll see in a minute. That means that we'll get our standard angles, but they're flipped now, if you will. So using this little piece of information here with the atan 2 method, let's go ahead and put together a very simple illustration. So how about we say we have a box, a perfect square. And let's say that the center of this perfect square is at 25 in X and 25 pixels down in Y. Okay? Now, what I'm going to do is, well, all right, this isn't going to look great, but I'll do my best. Not bad, not bad. All right. Again, we're going to say that as we're calculating our angles, 0 is going to start off over here, and our radian angles are going to increment as we go around that way, okay? Clockwise direction. So what I want to do is calculate the angle that we get if we wanted to figure out what this corner was, okay? Or if there was a ball that was perfectly in line, okay? If either way, whichever way you want to look at it. And I might jump back and forth between saying corner of the box or ball. Now, let's undo that. Okay, good enough. So that means this angle should turn out being what? Well, it should turn out to be 45 degrees, but we're going to have to look at that in radians, so we're going to be looking at pi divided by 4. Again, up here, 45 degrees, pi divided by 4. So let's take a look at this. What's the coordinate of this spot on the box? Well, we have gone in X backwards, and we've gone in Y. I'll just use this little arrow right here for me. Also backwards, or up towards the top. So both X and Y have gotten smaller. They've decremented, okay, in screen space. So let's say that, and since this is a perfect square, these numbers are going to be the same. They've both decremented the same amount. So let's say that we are located at 23x, 23y. Makes sense. Sounds fair. Okay, so now, very teeny box, of course. So now let's go ahead and look at what we need to do so that atan2 is going to return the proper number. So we now have two different points, but again, we need to assume that the box is located at 0, 0. So what we're going to do is take the box's coordinates away from our marker, or our upper left-hand corner in this case. So it's going to be marker or corner minus box. So x would be 23 minus 25, and y would be 23 minus 25. And this would give us a result of -2, -2. Okay? Now, what we want to do is plug this into atan2, but again, you're going to have to make sure y is done first. So Logan, what I'd like for us to do is let's go ahead and jump over to Visual Studio, and let's just set up a very simple scenario that'll give atan2 for -2, -2, but add pi to it so that we start off at 0 being on the left-hand side.
Right. All right, let's jump over to Visual Studio, and for the purpose of this demo, start a new console application. And then inside this application, do you want to, we could throw in a console read line.
Yes, the most famous line of them all.
Just so that we can see what the output was without the app closing. Now, we want to get the result of atan2 for the points -2 and -2.
Right.
So what I'll do is I'll store those in a variable. I'll make a double called angle, and we'll initialize that to the result of math.atan2. And then we need to feed it a point described as y.
And you'll see there that it's looking for the y first and then the x.
Since they're the same in this case, we'll do -2y and -2x.
And you know what? Thinking about it, don't add pi on yet. Yeah, let's go ahead and write that out so that they can see the result is a little bit different than they might be expecting.
All right, well, we'll write out the angle, and everything looks good. So if we run, this is the result we get, -2.3 and some numbers.
So we don't start with 0 being on the left-hand side, do we? Interesting.
Well, this is due to the way atan2 itself works. The atan2 method is going to return its results along the period of -pi to +pi. So that's going to be your full range.
So let's go ahead and add pi to this so that instead of -pi, if we add pi to it, we're at 0 for our starting point.
And then if we use that same range, because going -pi to +pi is an overall difference of 2 pi. The problem is it starts at -pi, and we want our diagram to start at 0.
Right.
Now if we add pi to that, pi plus -pi is going to be 0, and pi plus pi is going to be 2 pi. We have our full circle described in positive numbers.
Exactly. So let's go ahead and run this and see if we get, all right, 0.785. Ooh, that looks mighty delicious. And why do I say that? Let's bring up the calculator real quick. Now, we said that a 45-degree angle was a quarter of pi. So let's go ahead and do pi divided by 4.
All right, so there's pi. If we divide that by 4, our result is 0.7. Let's compare this to the output, 0.75, or 0.875, 0.875.
0.785.
785. Wow, okay, yeah.
You're doing like I normally do, flipping the numbers.
This is why I make computers do math for me.
Exactly. Okay, beautiful. So that we can see, back over here, we got 0.785, or 45 degrees if we were to convert that into degrees. Let's go ahead and do one more, just so that we can prove two angles here. So if I was to go straight up and down, okay, I'm going to push this all the way up here so we can see better. So what is this going to be? Well, this is going to be x being, well, y is going to be down just as far, okay? So y is going to continue to be, let's see, 23. So it's going to be 25 by 23. Because x has come over, y is going to be just as far down as right here, and x has now come back over to line up with this guy, putting us right there as we draw our little triangle in there. Okay, so now we have 25, 23. Let's go ahead and figure that out again. So again, over here, 25, minus the box, 25, comma, and now, not looking to do that yet, 1 second, comma, 23 for the top edge of the wall, or it could be the ball or whatever you're looking to get the angle from the center of this box, minus, and again, 25, which is y for the box, and now we end up with 0, comma, negative 2. Now let's put that into A tan 2, so A tan 2 is going to look like this. A tan 2, y comes first, so minus 2, comma 0. This guy right here better give us 90 degrees, but it's giving us a result in radians. And if we were to take a look at 0.785, if you were to double that, because, what is 90? 45 and 45. So we got two 45-degree angles in there. If you were to double 0.785, what are you going to have? About 1.5, yada, yada. So let's go ahead and do A tan 2 for negative 2 and 0.
All right. So going back to our quick demo app. Now we need negative 2 and 0. So negative 2 is y, 0 is x. If we run this and get the result, we have 1.57 some numbers.
So leave that up, and let's go ahead and launch Mr. Calculator. And once again, this is a half pi, so let's do pi divided by 2.
All right, there's pi. Divide by 2 results in 1.5707 and so on.
Beautiful, and the numbers match. So let's go ahead and close this guy out real quick. Close this guy out. Let's jump back over into here. So now we've got 1.5. Notice we're starting to establish a range, okay? And that's what's going to happen. We're basically going to establish these ranges as I was demonstrating back over here. So then we can turn around and say, okay, if the result we got fell between this and this range, then we must have hit the top wall. Or if it fell between this and this range, it must have hit the right wall. So on and so forth. Okay, Logan, is there anything else you want to add to this?
I think you'd already touched on the whole crossover problem of on the left side we have the problem of crossing from 2 pi back over to 0 within the range. So now that messes up our range. We can't say, well, if something is greater than 2 pi but less than 0, it would mess up the range in between the two. But what happens here, though, is since we have offset the entire range, we have all positive values up until that point, or even including that point. The problem is just crossing back to 0. Since we have all the other sides easily identifiable, easy to find the ranges, we can just assume the left side by process of elimination. If we have not hit the top, right, or bottom side.
If we're not in here, and we're not in here, then we better be in here, because if we're not in here, then did we really collide? You know what I'm saying? So basically, that's what we're looking at. So yeah, that's the nice thing about having it to where we flip on only one side. If they don't go in there and add that pi offset in there so that we start with 0 over there and we just go negative pi to pi, then they get to flip twice. And now they have a much more interesting problem to solve. Doing it this way makes things a whole lot easier. All right, anything else, Logan?
No, I think that sums it up.
All right, so again, this is just a real quick look at the math involved that we're going to be using. As you can see, there's nothing sophisticated to it. You don't really have to understand, how to use tangent and all that good stuff. I mean, the bottom line is A tan 2 is going to do all the work for you. For those of you that are familiar with trig, and you know that when, figuring up angles that can run all the way around in the 4 quadrants, how you have to add 180 or add 360 depending on what quadrant you're all in and all that good stuff. A tan 2 takes care of all of that for you, which is awesome. So with all that being said, this will be popping up in just a bit as we go through our proof of concept for BattleBlocks. And with that, let's go and get started on BattleBlocks.